Hello and welcome to this lecture on examples with involving expectations for discrete random variables. I will primarily use indicator random variables and show you two examples where the property of linearity of expectation along with the use of indicator random variables simplifies some of the computations. Okay, so this is a powerful sort of method. It's used across the board in various problems. Hopefully it will be of interest to you and you will enjoy it. Okay, let's get started. Okay, so the first example we look at is actually a very simple example. So let's say it's actually binomial distribution. Using indicator random variables. Okay, so you see it's a very simple sort of idea. Okay, so I'll put this in brackets. So basically what I'll do is I'll define, I will do n Bernoulli trials. What is a Bernoulli trial? You can think of it as tossing a coin. Probability of heads equals, let's say, p. Okay, n Bernoulli trials, and heads is the, okay, so I'll say probability of heads. Heads is basically success. Okay, so I'm doing n independent Bernoulli trials. So those are all things very important to write down. Independent Bernoulli trials, and each trial has a success probability of p. Okay, so let's say so xi is 1 if ith trial is success and is 0 otherwise. Okay, so what do I mean by this? I'm doing n coin tosses. If the ith toss is a head, I'm going to say this xi random variable is 1, otherwise I'm going to say it's 0. Okay, so this is an indicator random variable, right? Okay, so it indicates whether or not the ith trial was successful. Okay, so this xi is an indicator random variable. It indicates whether or not the ith trial was a success. Okay, so now what is my binomial random variable? So I'm going to define x as the number of successes in n trials. Okay, so in these n Bernoulli trials, how many successes I had, that I denote as x. We know very well that this is a binomial with parameters n and p. Okay, so we've studied this several times before, and you might also remember or know that this x can be written as x1 plus x2 plus so on till xn. Okay, so if you add up these n indicator random variables, you end up getting the binomial random variable, which is the number of successes. You can see clearly, right? So x1 is 0 means it was not a success. x1 is 1 means it was a success. So every time you have a 1 in the sum, it indicates a success in that trial. So you add up all these random variables, you will get the number of successes. Okay, so the number of successes can also be written like this. Okay, it's a very simple idea. So now we know very well that the expectation of x for a Bernoulli random variable is n times p. So these are formulae that you might remember, and variance of x is n times p times 1 minus p. Okay, so this is something you might remember from the time you studied binomial distribution. So one can use these indicator random variables, this writing of x in terms of the sum of n independent indicator random variables, to quickly establish these kind of relationships. Okay, so I'm going to start by showing you how that is done. So if you want to do expected value of x, okay, so expectation, you can think of it as like some sort of an operator. Okay, so I have a equation involving random variables. I can take expectations on both sides. Okay, so taking expectations on both sides, okay, so you can see expected value of x is written as expected value of x1 plus x2 plus xn. Okay, so now, okay, this is easy enough to write, but it turns out expected value is a linear operator. Okay, so it distributes over addition. So if you have expected value of x1 plus x2, it is the same as expected value of x1 plus expected value of x2. So you use linearity of expectation to get this. Okay, so here I've used linearity of expectation. Okay, so now in this case x1 and x2 and all that are additionally independent, but that is not really needed. Okay, even if the xi's are not independent, you can do this. In the next example we'll see, we'll exploit that situation, but right now anyway linearity works either way, so we do that. So now what is the big advantage with this kind of thing? The reason is, see, if you want to find expected value of xi, it's very easy. It's a random variable that takes just two values, 0 and 1. So it is 1 times probability that xi is 1 plus 0 times probability that xi is 0. Okay, so this simply evaluates to probability that xi is 1. What's the probability of success? And that's just p. Okay, so expected value of xi is p for every i. Okay, so this is just simply p plus p plus p n times, and that is just n times p. Okay, so a very quick derivation for the mean value or expected value of binomial distribution. So what about variance? For variance you have to do a little bit more of work. Okay, so if you want to do expected value of x squared, you will get expected value of x1 plus x2 plus so on till xn whole squared. Okay, so now the squaring is not a linear operation. I can't really distribute over the multiplication, but I can expand the squaring. So how do you expand the squaring? So you write it as x1 squared plus x2 squared plus so on till xn squared. Okay, so you just multiply these terms out. Then what are the additional terms you will get? You will get x1 times x2 plus x1 times x3 plus so on till x1 times xn. Okay, remember I'm multiplying these two things, x1 plus x2 plus xn times x1 plus x2 plus xn. Okay, so you'll get these terms. Okay, that gives you the square terms, x1 square, x2 square, and then x1 will multiply x2, x1 will multiply x3, so on till xn. That will give you the next term, and then x2 will multiply x1, x2 will multiply x3, etc. So you'll get x2 x1 plus x2 x3 plus so on till x2 xn. Okay, so the point is there are n terms here. How many terms are here? N minus 1 terms. Okay, so x1 multiplies everything other than x1 itself. So likewise here there are n minus 1 terms. So this will go on and on till you have xn. xn x1, xn x2 plus dot 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 xn xn minus 1. So this is again n minus 1 terms. Okay, and then you can put a close bracket here to indicate that this is expectation. Okay, so when you multiply it out you get something like this. So now you distribute the expectation. Okay, so this becomes expected value of x1 squared plus expected value of x2 squared plus so on till expected value of xn squared. So here I use linearity of expectation. Okay, and then you have all these terms x1 x2 plus dot 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 dot. I'll write all the way down to the last term, which is xn xn minus 1. How many such terms do I have here? So here I have n terms. Here I have n times n minus 1 terms. Right, all of them together I can group. Okay, and I used linearity of expectation. So how did I get n times n minus 1? So you see there are n minus 1 terms here, and then n minus 1 terms here, so on till n minus 1 terms here. How many such things are there? N, from x1, x2 to xn. So you have n of those, so n times n minus 1. Okay, so if you look at x1 squared, okay, remember x1 is just an indicator random variable. It takes value 0 with probability something, 1 with probability something. Now if you square it, you will again get the same sort of random variable, right? So it's going to be 1. So if I can cut actually xi squared, it's going to be 1. 1 squared is just 1. 1 if ith trial is success. and 0 else. It's the same thing. I mean, xi squared and xi are exactly the same because xi just takes 0 and 1. So that's very useful. So if you actually compute expected value of xi squared, you'll simply get p again. Okay, the same calculation as before. Now what about x1, x2 or any other xi, xj? Okay, so if you want to find expected value of xi, xj for I not equal to j, okay, I and j are not equal. Say for instance x1, x2 or x1, x3. So in this case I know x1 and xi and xj are independent. Okay, so if they are independent, so if I not equal to j, xi and xj are independent. Remember in the previous case here, expected value of xi squared you will get if I is equal to j. If I is equal to j, xi and xi are not independent. You have to calculate the xi squared carefully. But if I is not equal to j, expected value of xi and xj, you know xi and xj are independent. So once they are independent, you can do the calculation very easily. So this becomes expected value of xi times expected value of xj. Now what is expected value of xi? It's p times p, that's just p squared. Okay. So hopefully you see the calculation here. So expected value of xi squared is p, expected value of xi, xj is p squared for I is not equal to j. Okay. So these n terms correspond to xi squared, right? These n terms correspond to xi squared. These n into n minus 1 terms are xi, xj for I not equal to j. Okay. So now you go in and use the same formula here. So this becomes equal to n times p, right? Expected value of xi squared is p. We had that right there. And then plus n times n minus 1 times expected value of xi, xj, which is p squared. Okay, so you get np minus np squared plus n squared p squared. Okay, so I've just expanded this and written it in a different way. So that is expected value of x squared. Okay, what is variance of x? Variance of x is expected value of x squared minus expected value of x the whole squared. So now expected value of x squared I calculated as this from above. Okay, and then what is expected value of x the whole squared? N times p the whole squared. Okay, so these two will cancel. Okay, and you simply get variance to be np times 1 minus p. You can pull np common out of these two things and you get np into 1 minus p. Okay, so this is the first example I wanted to do, and hopefully this illustrates for you the ways in which you can use indicator random variables in a simple way. In this particular case, you also ended up having the independent trials, so maybe some of it was obvious, but nevertheless, I think if you directly calculate with the binomial distribution, you need to do some summations and all that very carefully for deriving these formulae. So getting to do it through the indicator random variable route is also very, very important. Okay. So the next example we'll see will be slightly more complicated than this one. We'll once again use the indicator random variables, but we will not have independence. Okay. So that example is balls on bins, our favorite example from the discrete world is resurrected again. So let's say you throw m balls into n bins. Okay, so once again at random, independently. Okay, so every ball is thrown uniformly at random into any of these n bins, and two different balls, what happens is independent of each other. Okay, so I'm going to define a random variable x as the number of empty bins. Okay, so you throw all these balls into these bins, and finally you count up how many bins are empty, and that's your random variable x. Okay, so it turns out this is not quite easy to study. This is not a random variable that's very easy to study. For instance, you could, I mean, there are maybe some extreme cases you can study a bit more easily, but nevertheless, this is a slightly difficult random variable to get your hands around. Okay, so one of the things is when you have a random variable which maybe the distribution is difficult to write down or difficult to get some intuition about, one of the things to do is to compute its expected value. Okay, you compute its expected value, maybe the expected value of x squared you compute, or the variance of x you compute. If you can compute those things, you get a rough idea of what the random variable is going to look like. Okay, particularly if you can find the expected value and variance, it turns out you can say a lot of things about the range at which the random variable will take values with high probability and all that. Okay, so all of that is useful in various applications, and let's see how to do expected value for this. Okay, so it turns out finding expected value of this is quite easy. Okay, so what do? You use indicator random variables. Okay, so I have bin 1, bin 2, so on till bin n. Okay, and I will have x1, x2, so on till xn be indicator random variables indicating whether or not the ith bin is empty. So xi is going to be 1 if bin I is empty. It's going to be 0 otherwise. Okay, so xi is an indicator random variable. It takes the value 1 if the ith bin is empty. After you've thrown these m balls into n bins, you go look at the first bin. If the first bin is empty, you say that the x1 random variable is 1, otherwise it is 0. Okay, so that's what happens in this experiment. That's how this random variable xi is defined. Now, in terms of these xi's, these indicator random variables, one can write down x quite easily. So, what is x? X is x1 plus x2 plus so on till xn. Okay. So, I mean, this situation at this point looks so similar to the binomial Bernoulli example we had previously, but the crucial difference is these xi's are not independent. Okay, so remember that xi's, xi and xj for I not equal to j are not independent. So we know this, you can calculate this and convince yourself that this is true in so many different ways. So also intuitively you can see. So supposing I tell you that bin 1 was empty, okay, the probability that bin 2 is empty is going to change, right? So because bin 1 is already empty, there are m balls that are going to be thrown only into n minus 1 bins, so there's going to be a higher probability that bin 2, lower probability that bin 2 is going to be empty than otherwise. Okay, so things are going to change. You can also establish this very precisely. You can calculate the probabilities, etc., etc. Okay, so they're not independent, but nevertheless, one can find probability that xi is equal to 1. Okay, so what is the probability that the ith bin is empty? Okay, so that's not too difficult to do. So the ith, what is the probability that a particular bin, the first bin, let's say, is empty, is that every ball should land in any of the other n minus 1 bins. It should never land in the first bin. Okay, and every ball is independent. So for every ball, the probability that it lands in any of the other bins is n minus 1 by n. This raised to the power m is your answer. Okay, so what is this? This is the probability that a ball does not fall in bin I. Right, so that's the probability that a ball does not fall into bin I, and I want every single ball of the m balls to not fall in bin I. So probability that xi equal to 1, the bin I is empty, is n minus 1 by n raised to the power m. You can also write it like this, 1 minus 1 by n to the power m, if you like. Okay, so that's the answer. Okay, so hopefully you understood how that works. And so this is the same for any bin, for any I, this is true. Okay, any I, this is true. So probability that xi is 1 is 1 minus 1 by n power m. Probability that xj is 1 is also 1 minus 1 by n power m. Okay, so it turns out one can also find other probabilities. So for instance, for I not equal to j, what's the probability that xi is 1 and xj is 1? Okay, so what does this tell you? Both bins I and j are empty. Okay, so it turns out this is also not too bad to calculate. What's the probability that both bin I and bin j are empty? Every ball, okay, every ball that you throw should not fall into either bin I or bin j. It's allowed to fall only into the other n minus 2 bins. So using the same sort of logic, you see this works out as n minus 2 by n raised to the power m. So 1 minus 2 by n raised to the power m. Okay, so right off the bat, you can see that this is not equal to probability of xi equals 1 times probability that xj is equal to 1. Okay, so what is this guy? This guy is 1 minus 1 by n power m times 1 minus 1 by n power m. If you want to write it as power m, this will be equal to 1 minus 2 by n plus 1 by n squared power m. Okay, which is clearly not equal to 1 minus 2 by n power m. Okay, so it turns out there's one overcounting here which gets rid of this problem. So xi and xj are not independent. So this is a proof for why xi and xj are not independent. If they were independent, this would be true, but they are not independent. But even though they're not independent, you can calculate just with xi and xj, you can calculate their probabilities very easily. Okay, so this is something important to remember. So now let's come back to our original problem of number of empty bins. Okay, so when you want to do number of empty bins, like I said, probability distribution of x is a little bit more complicated to write down, but expected value of x is not too bad. Okay, so expected value of x is expected value of x1 plus x2 plus so on till xn. Now we use linearity of expectation. Okay, so a lot of people who see this for the first time always ask this question, but x1 and x2 and all that are not independent. How can you use linearity of expectation? It's precisely, be convinced it's true. Linearity of expectation is always true. Okay, linearity of expectation is true for dependent random variables also. Arbitrary dependence is possible as long as you have addition. Expectation will distribute over addition. Okay, so it's a linear operator. The dependence or independence of the xi's don't matter at all for the linearity of expectation to work. Okay, remember that. That's a very important thing to remember. So once you knew this, you're done. Okay, so why is that? Because I know probability of xi is 1. So what is expected value of xi? It's easy to calculate. It's going to be 1 minus 1 by n power m. Okay, so why is that true? Why is the expected value this? So what is expected value of xi? Is 1 times probability that xi is 1 plus 0 times probability that xi is 0. So which is nothing but probability that xi is 1. So this is another fact which you should remember for indicator random variables. For any indicator random variable, its expectation is simply equal to the probability that it's equal to 1. Okay, so it's very easy to see why that's true. It takes just two values, 0 and 1, and probability that it takes the value 1 is simply the expectation. Okay, so this we saw already is 1 minus 1 by n power m. So that's true. Okay, so what is each i? The expected value is simply 1 minus 1 by n power m. So here you have n such terms. So it is n times 1 minus 1 by n power m. Okay, so even though the actual distribution of x might be difficult to write down, you can find its expectation. Okay, so this is also an interesting fact to remember as you go forward studying more probability. A random variable might be defined in a very complicated way. Quite often its expectation is easy to find. Okay, so as long as it's composed of some smaller random variables which you can handle in some sense, you can find its expectation. Maybe not very easily, but quite often it ends up being an easy expression to write down. Okay, so the next thing I'm going to show you is what to do with say variance of x or expected value of x squared. Okay, so expected value of x squared and variance are, I mean, more or less equivalent in some sense. I know expected value of x. If I know expected value of x squared, I also know its variance. Okay, so how do I find expected value of x squared? We can use the same trick once again. Okay, so this is expected value of x1 plus x2 plus so on till xn squared. And now you again expand this guy, right? I'm going to use linearity of expectation. Even though there's also a dependency, I can use linearity of expectation. We have x1 squared plus x2 squared plus so on till xn squared plus, you know, x1, x2 plus so on till you saw before xn minus 1. Okay, see these, there'll be n terms here. There will be n times n minus 1 terms here. Okay, hopefully you see that. Okay, this is the same thing as what I did before, exact same simplification. So now we use linearity of expectation. If you do that, this will simply become expected value of x1 squared plus expected value of x2 squared plus so on till expected value of xn squared. Okay, and then you will have all these other terms, expected value of x1, x2 plus dot 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 expected value of xn minus 1. Okay, Hopefully you can, hopefully this is easy. Okay, so now what is expected value of xi squared? Remember, expected value of xi and expected value of xi squared are the same, right? It's the same as expected value of xi. So again, this is true for any indicator random variable. Okay, because xi takes just value 0 and 1. If you square it or cube it or anything, nothing is going to change. You'll get the same probability. So that's okay. This is easy to handle. And what is expected value of xi times xj? Okay, remember. So here, what is the expected value of xi xj? Okay, so I'm multiplying xi and xj, right? So remember, xi and xj take two values, 0 or 1. Okay, so if you write down xi xj, they take 0 0 0 1 1 0 1 1. What will happen when you multiply xi and xj? All these guys will become 0. This will be the only thing that's left. Okay, so if you do expected value of xi xj, you will get 1 times probability that xi equals 1 comma xj equals 1. Both xi and xj are 1 plus 0 times various other things. Okay, so probability of xi equal to 0, all the other things, right? So xj equal to 0 plus 0 times probability of xi equal to 0, xj equal to 1, okay, plus another 0 times probability of xi equal to 1, xj equal to 0. Okay, so all these terms will go away and you will be just left with probability of xi equal to 1, xj equal to 1. Okay, so here is another interesting thing about indicator random variables. The only thing we used here is indicator random variable. I don't care about dependence or anything like that. So expected value of xi xj is equal to probability that xi equal to 1 comma xj equal to 1. So this is again a fact which is true for any indicator random variable, and you can also extend this. Okay, xi, xj, xk, etc. Keep on extending this. Will simply be the probability that all of them take the value 1. All of them individually, jointly take the value 1. Okay, so this we have already calculated, right? So we just went and did this calculation here, xi xj equal to 1, and that is simply 1 minus 2 by n power m. Okay, so that is now easy to write down. So here you will see that there are n terms here, and all of them are equal to, each equals 1 minus 1 by n power m. There are n into n minus 1 terms here, and each equals 1 minus 2 by n power m. Okay, so you see I can write this as n times 1 minus 1 by n power m minus plus n into n minus 1 times 1 minus 2 by n raised to the power m. Okay, so that's the little trick involved in this calculation. Main trick is linearity of expectation, and the fact that indicator random variables pretty much tell you the expectation is the same as joint probability calculation for both of them taking the value 1. Okay, so for this problem, which was once again I want to reaffirm that we never found the distribution of x, right? For the number of empty bins, finding the distribution of x is a little bit more painful. And if you want to calculate the expected value of x squared through that route, find the distribution of x first and then use the formula for expectation. It's not that easy. Okay, on the other hand, using indicator random variables and using the linearity of expectation and using properties of indicators, one can very quickly get to the answer. Okay, so I will leave the computation of variance as an exercise. It's quite easy to do. I will leave it as an exercise to you to finish up. Okay, this is the end of the lecture on expectations for calculation of expectations for discrete random variables, slightly more complicated cases involving indicator random variables. Hopefully you like this lecture, and this will also be the last lecture as far as examples go in this course, and this is the last week of the course. And if you've managed to come along this far in this course, I'm really happy that you managed to do so. Hope you enjoyed this course. Thank you very much for being a part of it. Bye bye.